All right. So we're going to do some code meandering, and I have no idea where we're going to go. But what I tend to find as a fun experiment is to bring up Mentor. And usually we look at Mentor summaries. This is sort of the more public version of Mentor where we look at various repos that we've dropped in this and some high profile customers, and some of our investors and stuff will hop onto this thing and then they'll search through this list of repos and we'll talk about stuff. But the team is actually working on some pretty cool things. And it hasn't gone live yet. So I want to look at that. How do I turn this thing off? Top chat. I want to... I'm such a noob. Okay. Who knows? So we're going to look at test because test has some stuff that's not live yet. And in particular, I want to look. I was meandering through this, and I think I came across TensorFlow. Yeah. All right. So here's TensorFlow. As we know and love, TensorFlow historically is a machine learning, at least my peripheral, very basic understanding of TensorFlow. It is a machine learning framework that came out of Google, and it, I think, largely is written in C++. Going back to that whole point about C++ and C maybe secretly run the world. More evidence. But the interface into TensorFlow is oftentimes in Python. Okay, so we can say that Python is also going to run some parts of the world. Okay, so here's TensorFlow, and it's pretty good score, all that stuff. We can look at the lifetime graphs. Wow, that was pretty fast. Wow, that is... Okay. The team is... I mentioned to the team that I was having some performance stuff, and woo-wee, I guess they took that seriously. I love it. The other thing that we added, which I just want to talk about for a second, is we have this new mentor value tab, which then helps you calculate essentially the approximate savings that you get by using Mentor to help figure out the issues that it's finding and the time that you're saving for developers and total cost and stuff, all that. So it's just fun little stuff, I think, to make it potentially more easier to understand its value. All right. So all that stuff aside, let's go back to, man, I really enjoy seeing that. Hold on. I'm going to use the down arrow key. So, uh-oh. Did they break the down arrow keys? Yeah, it looks like maybe down arrow keys, guys. Okay, hold on. Let me just... Oh, maybe it's because... that could be it. Okay, let me just... I just want to check something out here. Whoa. Guys, this is fast. Okay, so this just... To give you some context, this just... I think that was put on test. This is our internal testing site. And so I haven't really had a chance to play around with this. So I just want to take a moment to see. Wow, the redraw. I don't know what that is. wow, the redraw speed is this is pretty great. Good job, team. Well done. Yeah. Okay. Just having a little bit of fun watching this thing redraw so quickly. I mean, it would redraw before, but I think many of you remember it was like kind of taking its time, whereas now, boom. I mean, that is some. Okay, now there's the test. This is the big one. This is the one that I actually kind of complained a little bit about. It was when we brought up code and we would try to move the panes around a little bit, and it would kind of freeze the whole thing. It would like freeze the stream, the video, and everything. So we're going to try this. And I haven't tried this. So we're going to look at it together for the first time. Here we go. Whoa, boy. Oh my goodness. What repo? Oh, is this ClickHouse? ClickHouse. Oh boy. ClickHouse, guys. Okay, right. No judgy. No judgy. Practice empathy, Goju. Okay, I'm not judging. I just prefer my control expressions to not be this long. But I understand. Sometimes you got to just try to get stuff done, and you can push maybe not the best code out. All right, here we go. Okay, so it's going to think about this. It's probably going to take it a second or two because it's got to load quite a bit. All right, now this is where we would usually get the major crash out as I try to resize this. And you can see it's still messing with the video, like it's stuttering, right? Like you can see that. So more work to do. Let's just try to move it like a little bit. Yeah, it's... So you can see after a couple seconds, it kind of smoothed itself out. And what's great too is as I test this, I know the Merlians will be watching this, and so then they can see that, yeah, there's some more work to do. All right, so we looked at ClickHouse before, and we kind of know that they have these things. By the way, yeah, generally speaking, let's not do this. And for those of you that don't know what this is, I think if you go to GTT, there's some videos in here. I don't know. I suspect if you search on ClickHouse, you can probably find ones that talk about. Yeah, maybe this one. I suspect you can find it. Anyway, we're not going to look at that today. Today, we're going to look at TensorFlow. Because I feel like this is a quadruple whammy in that, one, it's related to machine learning. So that's cool. Two, it's from Google. And in theory, what Google's writing, I mean, they're supposed to be some of the best software developers in the world, right? So they should be writing really good code. And yeah, overall, I think that you can see that the code they're producing, at least according to Mentor, seems to think it's pretty good. And again, 4.1 million lines of code. This is not a small repository. This is not something that's super easy to do and keep a relatively good score, and also to keep the anomalies down. So let's turn the anomalies off for a second. We're just going to talk about the repo overall, and then we're going to zoom in on just one issue, and we're going to talk about maybe trying to fix it and the ramifications. of this particular issue, because it's a bit unusual and actually kind of interesting in that well, you'll see. So here's the score, and it starts out around 800 and then it dips down to 650, which is not super great, but then they recover, right? And then it stays pretty healthy. They have some dip here, and I suspect if we turn the issues back on, we can see there's this jump in issues, and then they start to recover from this dip. But the issues are really kind of, I think it's like the first time that you see proportionally the issues overtake the lines of code, right? So this teal line is basically the lines of code, and the issues is the red line. And so you're seeing sort of this proportional relationship. And then right about this point, the issues overtakes the lines of code in terms of its proportional relationship to one another. The entire time before that, it stayed below it. So at this point, something's changing, and not for the best. It's changing in a way that is maybe not like a good thing. So, and you can kind of see this. We have a number of these notable things. These are going to be like complicated, long control expressions. And then the anomalies themselves, these are going to be things where it's like it doesn't necessarily mean that it's complicated in terms of length, but it's stuff that you probably want to fix because it's complicated. This is not the issue that I want us to look at, but let's just take a look at this. Like, for example, this one, I don't know what Mentor's going to say, but I can say that this is kind of freaking me out in a couple different ways. The first is you're doing this division by this cost window, and whenever I see these divisions in my mind, I think something like division by 0, and then I think, uh-oh, is that a possibility? And probably not, but I don't know. It's at least on my mind. But the bigger one is this part right here, this trial mod window size. So I don't know exactly what they're trying to do here. But this is the modulo operator, which is basically, you can kind of think of it as it's like division, except the difference is it's going to give you the remainder. So let's say that trial is the number 5, and this is the mod operator, and then let's say window size is 3. Then what it's going to do is it's going to say 5 divided by 3, and it's going to say, yeah, that's 1, essentially, with a remainder of 2. And then what it will give back as the answer is the number 2. So just think of mod as it just gives you the remainder. It's always the remainder. And the remainder for any number that you do division on is any number between 0 and through n minus 1. Right? So let's just write this down really quickly. So when we're doing modulus, who knows? Different people call it different things, but it's this operator, and it is the result of modulo is 0 to n minus 1. This is inclusive. How do we represent inclusivity again? It's like this, I think. Yeah. Okay, mathematical inclusivity. So the range is 0 to n minus 1. So in this case, we can say example trial equals, what did we say? 5. Window size equals 3. Then trial, mod window size is going to be equal to 5. Oh, sorry. Mod 3 equals essentially to 2. Okay, that's basically what we're getting here. Now notice that if trial happens to be 3 and window size is 3, then this will be 0, right? Make sense? Because there's no remainder. Now, in this case, that's probably not a problem. My speculation, given this cost window array, because C++ has 0-based indexing for its arrays, and so there'll probably be a 0th element. But I just wanted to share this because sometimes people will get confused about modulo returning 0, and it can return 0, and therefore you can have similar problems with it then being like in the denominator for division. So if this gave the value 0 and then you did just this, current cost divided by 0, then this would be an exception. And you would get division by 0, which is undefined, and the program would terminate. Okay. Cool. So this is looking at just a random anomaly, and Mentor doesn't necessarily like all this. And part of this is there's no bounds checking. This is just a raw array access, which could be out of bounds. So Mentor's probably not too happy about that. And then again, this could result in a value that's 0, and then that could result in a crash. So what does Mentor have to say about this? Okay. So the first part, the current cost divided by cost window, this expression divides current cost by an element from an array, cost window. The specific element selected is determined by this thing, which gives the remainder when trial is divided by window size. Yeah, so like we're talking about with modulo. This operation is typically used for cycling through an array. -1 minus result. Yes. Yeah, okay, that's another thing is, yeah, good on you, Mentor. I actually kind of missed this one. This 1 minus whatever will be done after all of this. And that's because these have higher operator precedence than subtraction does. To make this a little bit easier to understand, you'd probably put parens here. I actually almost made the mistake of thinking 1 minus current cost and then this division. And then after reading Mentor, it's like, hey, yeah, you're going to do the result from the division is subtracted. So it's letting you know, essentially, that this subtraction will be done last. You should probably put parens here just for extra clarity that you understand as the code writer, the operator precedence, so no one else like me is getting confused when they look at it. Okay, comparison is less than tolerance. The results of subtraction is compared with a variable tolerance. If it is less than tolerance, the condition evaluates to true, and yada yada. Okay, so potential bugs. First thing, division by 0. Yes, so this is what I was saying, is whenever I see the stuff like this, the first thing that pops in my mind is, ooh, could be division by 0. I don't know. I don't love it because I would like to check to make sure this is not 0 first before just doing this. And I think that's probably, yeah, what Mentor's saying. So good on Mentor. You should probably, I agree. Array bounds, ensure window size is greater than 0, and cost window has at least window size. Yeah, I agree with that. It seems as though that's right. I forgot about this. There is this embedded potential division by 0 that could happen if window size is 0. This would just crash the program. So Mentor is right about that check. Where it says, where does it say it? I thought it said it. Right here. Ensure that window size is greater than 0. Yes. Because if it isn't, then you just crash the program. And window size, I could probably search for this. I was hoping I could just scan it. Let me just... Whoa. Yeah, I don't know. I just know that it's the min of these two things. So whatever this thing is, or this, whichever is smaller. Could it be 0? I don't know. Seems like it. Depends on what num trials. Yeah, we'd have to look at this. Okay, let's just keep going. Array bounds ensure that window size. Oh, yeah, I think I got that already. Greater than 0. Integer, overflow, underflow. Yes. Crash prevention, multiple division by 0 things. Yes. Okay. So Mentor is going to come and rewrite this. Yeah. Wow. I'm actually... I don't mean to sound super surprised or anything, but Mentor's results are not usually this good. This is actually pretty... Huh. Okay. Yeah, this is fairly robust, guys. I like it. Okay. Yeah, I think Mentor is doing a pretty good job here with this. It's got the check on this. It has like an additional check here. And it's throwing these different types of exceptions, which is pretty good. And then if everything passes, then it essentially allows us the result to perform this operation. Forms the operation side of the conditional here, this part, and then returns whether or not it is less than this tolerance amount. Cool. Okay. Yeah, I think that looks pretty reasonable. So yeah, good job, Mentor. I feel like this output has been beautified or something. Like actually, I'm gonna upvote this. This is a pretty reasonable. Interesting. Okay. Yeah. Okay. So there's one example of an anomaly that Mentor is working through, and now I want to. Oh, and we also added this age thing. I think this is pretty cool. You can search on the criticality of the issues, and then you can also search for the age. You can order by age. And I think this is super helpful. So you see which ones have been introduced more recently. Like, for example, this issue here was just introduced a day ago. This one's 9 days, and so on and so forth. You can see here, like, it's a few months. And then if we continue down, we see that some of these have been in for a year. And we keep going, and wow, we get some of these, they've been around for, yeah, a long time, 9 years. Should probably fix some of these. I think actually this is the issue that I was going to have us look at. I'm pretty sure this is it. Yeah, this is it. This is the one I wanted us to check out. Okay. We're going to move that a little bit. Take a look at this. Let's make this just a little bit bigger here so we can all see. All right. So this is our code. And I want to give us a moment to take a look at this and contemplate this before I start to talk about what I think about this and what I think about this code. I also want to share, too, that this, I believe, is in test code. So this is some test function, it seems. And there's some more. It's like this other test function. And yeah, just a whole bunch of these interesting tests. So I am well aware of this. I know we're looking at test code, and yeah, I would argue that test code is still code. Just like when you're trying to teach your children how to communicate, they're not just learning how to communicate from their teachers, they're also learning from their parents. And so even though the teachers, one might argue, well, that's where they should be learning, not from what the parents are saying, although that might be slightly misguided. The same argument I think can be true about code is, oh, well, the only code that really matters is the stuff that's in production. The test code is just test code. Yeah, I don't totally buy that. I mean, I do a little bit, and that test code is the code that is maybe not on the front lines, but on the other hand, the test code is what is helping us identify issues with the code. And then on top of that, people still learn from test code. And so if they look at code like this, then they may think, oh, well, this is acceptable, so then I can write code like this. Or minimally, they're just learning. And I lastly, I want to share that one of the most important things I think for us to be thinking about today, super important, especially in the vibe coding era that we live in, is I'm of the mind that it's far more important to be learning and growing than it is to be producing. Now, I'm not saying production and output and things like that don't matter. They certainly do, especially like in the startup life. But I think that a very simple analogy is this. By the way, this is my somewhat ironic use of the much greater than operator in mathematics. And that is the much greater than operator in mathematics. This is actually like a real, this is not pretend. This is a real operator. And much greater than operator in, there you go. This is, it's not a joke. This is this is really a thing. The symbol for much greater than is this. You heard it here first, or maybe not. Anyway, so this is a little bit of an insider joke. Is I generally argue that this operator has no business in formal mathematics, yet somehow it's part of the grammar for formal mathematics. And the reason why I say it has no business in formal mathematics is because what does it mean for something to be much greater than? What is that like? Is it 2 times more than the thing? Is it 10 times more than the thing? Is it 100 times? Like everybody could probably have a different definition of that. And who's to say that anybody's definition is wrong and somebody else's is right? This is why, yeah, like things of this nature that lack the ability to be defined precisely and are more hand wavy, like the word very. This is very important versus like this is important. Like what, for example, what is the difference between those two statements? What is something that's important but not very important, or vice versa, and who makes that decision? Therefore, that's why much greater than versus greater than is like anybody's guess. Anyway, this is me just poking fun at this silly operator. But I am trying to make the point that I think that reading is more important than writing in a general sense. And the argument here is the argument that people use when they are thinking about things like writing a book, or writing code, or writing music, writing plays, any of that stuff. Same thing as like playing football, playing a sport, running a marathon. One is the act of doing in like the official capacity. The other is sort of the art of rehearsing, practicing, learning. And I would argue that all the greats, this is a very strong claim, but I would argue that this is probably somewhat like a universal truth, which may go against kind of the salacious, sensational media, is people aren't just sort of born with greatness. They develop it. It's a skill. It's something they've learned. So all the people that you think that may be incredible communicators, it's probably that they've spent hundreds of thousands of hours practicing and refining their craft of communicating. People that you think are incredible athletes doing a specific type of thing, again, similar. It's not they just they came out of the womb, they've never seen chess before, they sat down at a chessboard and suddenly they're a grandmaster. It just doesn't make sense. Even if they have all those incredible neurons, there's still the learning piece that's going to go on. And this, I would argue, is true fundamentally of pretty much all activities. Any kind of activity that is skill-based, the skill is a learned phenomenon. It's not it just manifests itself. Therefore, in order to be great at anything, whether it's writing code, running marathons, creating movies, you likely need to spend more time practicing and learning about this thing than the actual doing of the thing. And I think there's a great quote that talks about how sports games are not won or lost on the game field. They're won or lost on the practice field. And I quite like this. I think that's a great way to think about this, at least for me personally. And the reason for that is it's really the preparation. That if you don't have an incredible amount of preparation in something before you go to do that thing, you're probably going to flounder quite a bit. So, with that in mind, when we go back to this code, even with this being test code, I'm still going to grade this code pretty critically because people learn from the test stuff. They learn from the practices. And so all the code should be held at a high standard. And I get it. I'm not saying that all code should be held at the same standard. I'm just saying that all code should probably be held at a high standard, especially for really high production quality systems like something like TensorFlow. Okay. Now, for those of you that are not familiar with machine learning, specifically things like neural networks, you may be looking at this and are scratching your head trying to understand what the heck is going on here. This is 1, 2, 3, 4, 5, 6 levels of looping to do this if statement. Why would you loop that much to perform this conditional? That seems like a lot, right? And this definitely goes against our never nesting rules. Now, I haven't looked deeply at this code, so I don't know for sure what exactly is going on. But my speculation is it's this. This is doing one matrix comparison to another matrix comparison. And each of the matrices that they're looking at has their rows, their columns, and then their depth. So they're essentially these three-dimensional cubes. So we've got our row, our column, and then this depth. This is one matrix, three-dimensional matrix. Then you got another one, which is our rows, or sorry, our columns, our rows, and our depth. And then this is like our second three-dimensional matrix. Now, there's a slight difference here. These are all related to output, and then this is patch, and then input. So I'm not exactly sure what's going on there. We'd have to look at this more closely, but this type of 6 for loop nesting is pretty common when you're doing large neural network analysis across two matrices. This is not like an unusual thing. And in fact, if you scroll up, you'll see here's another one. And I bet there's, oh, this is the top of the file. Okay. So we'll scroll down. So here's another one. Hold on. 1, 2, 3, 4, 5, 6, 7. Okay. That's a bit unusual. It's 6 is a pretty common. Whoa, look at this. You have embedded literals. Woo. This is breaking some of my rules. Okay. What is this? 1, 2, 3, 4, 5, 6, 7. You have 7 again. Okay. That's okay. So that's interesting. This is, I see. Okay. This outer loop is for the batches that you're going to do. So you still are having the embedded 6 loops, but this outer one is for the batches that you're going to run on. So, and for those of you that are working in machine learning, you probably know the batches are sort of like these various types of learning, and you can do batch mode and how many batches you have in each of these learning iterations or these learning epochs and stuff like that, right? So maybe this is what's going on here with this 7th for loop. But so you can see there's sort of like this pattern emerging, and that's not totally unusual to see. At least that's been my experience. Okay, cool. So we got some good examples of that. Now we can go back. Just out of curiosity, just wanna... Interesting. Okay. So now we'll go back to this code. I think we're right about here. All right. Now Mentor has highlighted this. And before we look at what Mentor is going to say, I think that it makes sense for us to look at this and try to observe a couple things. And from my perspective, when I was looking at this goes back to this whole notion of mastering the basics. We've spoken about this many times, right? So let's talk a little bit about this. Mastering the basics. Know the basics cold, and you'll likely be well off. And most of stuff is around the basics. Yeah, I think that's kind of the view that I hold. So when I'm looking at this expression, I'm just thinking about the basics. And when I look at this and then I consider the context of this being inside of 6 for loops, now I start thinking about this in a slightly different way. Is that this is no longer just a control expression that you might find out in the wild. This is now a control expression that has ramifications of being on a hot path or being something that can directly impact performance. And the reason for that is that you have something that is basically O of n to the 6th, right? Because it's like, here's O of n squared, cubed, quad, cent, so 6. So it's like O of n to the 6th. Because each one of these, like this outer loop is going to do this inner loop, the whole thing, each iteration. And then this one is going to do this inner loop for each iteration. So it's basically n to the 6th, which basically means this if statement inside of here could be executed a lot. And by a lot, it could be, let's just say, 1 billion times or more, depending on what n is out here. And if this is a large matrix, 1 billion is not outside of the realm of possibility, truthfully. And if you don't believe me, just put into your calculator. Here, we can actually do it. Let's see. What would it take for n to the 6th to have it blow up into something quite big? Where's the... I need like a more advanced calculator, I think. Can I do it here? Yeah, here we go. I can do it with this one. All right. So let's say we want 10. Let's just say that n is 10. Let's say 10 to the 6th. What does this give us? That only gives us 1 million. So if n is only 10, that's not going to cut it. Okay, so what if n is 100? I think we kind of already know the answer. This is going to do it. Here we go. Whoa, okay, we are there. There's 1,000, there's 1 million, there's 1 billion, there's 1 trillion. So if n is 100, we're going to get into a trillion iterations. So all we need is OD, for example, to be 100, and these other guys to be 100, and then this single expression could be executed 1 trillion times. Yep, just like that. Thus, the asymptotic growth and why we care about things like big O. Look at this. You're getting to learn 15 different fields of computer science with this single VOD. This is great. See what happens when Goju's feeling a little unwell is you get to meander all over the place. Okay, so now given that this thing can be executed upwards of 1 trillion times if any of these iterations are 100 or more, what does this mean for this control expression? So let's consider this for a moment. Let's just look at this control expression and let's just ask ourselves some very simple questions, like, without changing the semantic meaning of this control expression at all, the semantics are not going to change. Are there things that we could do to this control expression to improve its performance so that if it does get executed 1 trillion times, it's like just more efficient? Okay, so let me pause for just a moment and give people a second to think about this and ask this question. Just looking, so ignore all these for loops. Don't let this distract you now. We know that it's inside of this really intense nested looping structure, and it's on a very hot path. Ignore all that. Now just think about the implications of the control expression itself. And are there things that we could do for this control expression that could keep it so its semantics are identical to how it is right now, but so it potentially is more efficient? And the reason why we care about efficiency here is that, let's say that this thing invokes 100 millisecond overhead for the execution of this control expression. So 100 milliseconds times a trillion is going to be a noticeable performance degradation. Because I can tell you just right out of the top of my head that 100 milliseconds, 10 of those is 1,000 milliseconds. 1,000 milliseconds is 1 second. That just changes that number 1 trillion to 100 billion. Now, if I drop it 2 more down from 100 billion to just to 1 billion, I'm going to change it from 1 second to 100 seconds. So now it's going to take 100 seconds, and I still have to execute it 1 billion times. Now let's add 3 more zeros. So that's 1,000, 10,000, 100,000 seconds. And now I'm at 1 million. So 100,000 seconds, and I still have 1 million iterations to go. You can see how this quickly can, like, no joke. And this is part of the reason why machine learning training is so slow, why it takes so long. It's this. It's really this. It's the matrix multiply. It's the matrix operations that end up taking quite a bit of time. So if we can make this slightly better, the performance implications could be huge. That's doubly true by the fact that as we meandered a little bit in this code, we saw that, oh, look, we've seen this before. This was like right here. And I'm not sure, but okay, this one's slightly different. But you can see there's a lot of similarities. It's not exactly the same, but you know. So, and then here's another one. Not exactly the same, but okay, this one doesn't have it. That one's okay. So these ones like are a little bit better, but I think you likely get the point. So what could we do to make this slightly more efficient? And what we're doing here is we're just thinking about the basics. We're not trying to rewrite this in some massively elegant way. We're just going to stare at this the way it's written right now and then see, is there a way that we can do this potentially a little bit better? So I'm going to give you not like a full answer, but a little bit of a way that we can improve this, which is super, super simple. And it literally doesn't change really anything in terms of the original code. So it's literally only going to change just the control expression. So everything else can be exactly as it was. And the suggested change that I have is, again, going to be just related to mastering the basics. And I haven't worked through all of the logic to know for sure if I'm right about this, but it kind of makes sense in my head. Okay. So for those of you that are live stream, I'm just going to start to attack this. For those that are watching the VOD, you can pause it here if you want to think about this more before I give you at least one potential answer. Okay, so the first potential answer is eliminating some of these minuses, specifically these minus ones. The reason why I want to get rid of these minus ones is that they're static. I know exactly what they are. They're minus one every time. It's not a variable. It's like if you were to add one. So -1, +1, it's the same thing every time. And what I am looking to do is essentially just do a complexity reduction on this. And again, normally I wouldn't care. Normally, if this was just a free-floating control expression out in the middle of code, I don't care. But when it's embedded inside of 6 loops, and we just saw that this could be invoked 1 trillion times if the matrix is large, or I don't even know if 100 rows or 100 columns is large. In fact, I know for certain in many cases that is not large. And so it could be far larger than just 1 trillion calls. So doing a small amount of optimization on this is like, this is almost like supercoder heroics. You can be the hero coder by making a minor change on this. So in my mind, what I see is I see a recurring pattern of -1, -1, -1, -1. And in my head, I think, why not just get rid of this -1 and see what we can do about changing these comparisons? So one way to think about this is I think that I've got a -1 is greater than or equal to 0. And then what if I have just a and then something with 0? I don't want to do -1. Well, -1 is going to make a 1 smaller. And I'm checking to see if a is greater than or equal to 0. So what if I just drop the -1 and then I change it to just greater than 0? Like, does that work? So let's give a concrete example. Let's say that a is equal to 1. So then you'd have this 1 -1, which is equal to 0. 0 is greater than or equal to 0. This is true. True. Cool. Okay. So now we're going to make our change and instead say a, we're not going to do the -1, and we're just going to change greater than or equal to 0 to just 0. Now we're going to drop the 1 in here and ask, is 1 greater than 0? It is. That's still true. Okay, cool. That example worked. Now let's try this one. A is equal to 0. So 0 minus 1 is going to be equal to -1. -1 is greater than or equal to 0. This is false. Then a is equal to 0. 0 is greater than 0. That's false. Okay, cool. We haven't gone through the full testing of this, but it seems likely that we can probably do this. Now, why is this more efficient? Well, it's more efficient actually for 2 different reasons. And both of these reasons have to do with the basics. The first is you're doing a reduction of an operation, which is you're removing a subtraction operation from this expression, and that is just making it more efficient because that operation is just gone. On top of that, as we discussed in some of the prior episodes, less than is always more efficient than less than or equal to. Why? Because this is greater than. Greater than or equal to is greater than, and then it's equal to. This is 2 operations. This is 1 operation. Therefore, if you can change greater than or equal to just a greater than, you've also made it more efficient. You've actually made it efficient in two different ways by this one change. You've reduced a subtraction and you reduced a complexity of a comparison. And the semantics are the same. The semantics of this and the semantics of this, at least I think, are identical. We just made it better. That's pretty crazy, right? I mean, I think that's pretty crazy. And keep in mind, this is TensorFlow. We're not looking at computer science 101 code. We're looking at the open source of TensorFlow in their eigenspatial convolutions test CPP file. I mean, that sounds kind of fancy. But as we've discussed many times, a lot of this is just the basics. It's just the basics. Once you master the basics, it's like it looks like you have superpowers, but it's not. You just know the basics so well that it's just obvious. So, for example, I can kind of tell in some capacity that performance matters for them because they're using the pre-increment, not the post-increment on these, the post operations for the for loops. They're not being careless here and using post-increment. That's actually a very clear signal to me. And again, this is just a basic thing. You would kind of learn this in CS 101, the difference between pre-increment and post-increment, and the core difference being that pre-increment doesn't need to return a temporary. It just increments whatever the variable is, and then you have it. Whereas post-increment returns the variable in its unincremented, non-mutated way, and then it performs the increment operation. Therefore, the post-increment, by its nature, is more complicated. Very much like what we just discussed here. The greater than or equal to operation is just inherently more complicated than greater than. So it's a strength reduction to use greater than over greater than or equal to, very much like it's a strength reduction to use pre-increment over post-increment. Basic stuff. Not complicated. This is not advanced. And now we have just optimized, we have just improved the performance of production quality TensorFlow code. Good job, everybody. And we're not even done. We can take that same principle and apply it here. So we're going to drop this -1 and just change this guy to this. So we've got the second one. Now, these next two, it's more complicated. Now, this is where we have to slow down a second and really ask ourselves, is this going to go the way we want it to go? Now, the reason why we have to pause is that you'll notice that in both of these earlier ones, we're able to do a reduction of arithmetic complexity by eliminating subtraction, and then a reduction of the conditional complexity by eliminating greater than or equal to and reducing it just to greater than. But now we've got kind of the inverse going. Now we have a situation where if we drop this -1, we're going to have to do this, I think. And if we drop this -1, we're going to have to do this. So with these two, it was very obvious a win. It's a double win. With these two, it's not so obvious anymore. Because if we drop this -1, we now need to change this from being less than to less than or equal to, I think. And if we drop this -1, we have to make this less than or equal to. And so a quick example of that is, let's just do our simple math again. We'll say that R is equal to, how did I do this before? Oh, yeah, we were like ignoring the I part. So let's just say that R is equal to 1. Yeah. And then I think it needs to be, there's a 1. Yeah, okay. And then output rows is equal to 1. And so then R minus 1 is equal to 1 minus 1 is equal to 0. And then 0 is less than 1. We're just ignoring the I and j for now. So in this case, we have this. R is equal to 1, output rows is equal to 1. And then this is going to be 0 is less than 1. This is true. Okay. Now, I've got to just put this wrist guard thing on. Okay. Now, we are going to say R is equal to, oh, we already know that R is equal to 1. So we're going to say, we're going to change the expression to R is less than output rows, but we think we need to change it to less than or equal to because we're going to drop the -1. Okay. And so now we say R is equal to 1. And we have 1 minus 0. So that's equal to 1. And then we have 1 is less than 1. That would be false. But we also have 1 is equal to 1 because it's going to be both, right? It's going to be less than or equal to. And then 1 is equal to 1. That's true. And we just need one of these to be true. Okay. So let's just change this back to this. And so we see that, okay, this is true. All right. So now you can see how we've got to do kind of the opposite of what we did last time. Last time we did a reduction on the conditional and a reduction on the arithmetic. This time, in order to do a reduction on the arithmetic, we have to do an increase on the conditional strength to make it more conditional intensive. So in order to change this piece, what we have to do is we would get rid of this -1 like this, and then we would change these to this. Now the real question is this going to be beneficial? Is this going to make the code more efficient, less efficient, or unknown? And I think for this stream, what I'm going to do is pause here and not tell you the answer, and instead give all of the viewers the opportunity to contemplate this, to deliberate on this, and try to understand which is likely more efficient. This, which is the original, or this, which is the modified, or are they the same? Right? It's very clear that the original is more optimal when it's in this form. There's no debate here, or there should be no debate. because logically, we've just made this simpler in two different dimensions on both of these expressions. Even if we don't empirically show this, it should not be surprising to any of us, as long as we're thinking critically, that this must be at least as fast, if not faster, than the original code. And in fact, for the next stream, what I'll probably do is show the code running on my machine in the original form here, embedded inside of these 6 loops and iterating, let's just say like 1 billion times, and then showing the performance benefit. I can tell you without having written this code yet, but having written similar code, that unequivocally, this version will be at least the same performance as this. More likely than not, it will be faster. And depending on how many operations this is, this could be notably faster, notably being, in this case, 10 to 100 to 1,000 times faster. That's right. Just this change to this could ultimately make this original code 10 to 100 to 1,000 times faster because of the context. It's all the context of having these 6 for loops that it's embedded inside, which could result in upward of 1 trillion executions of this control expression. And we'll actually look at some of the data. I'll probably stop at the point to where it's like, I don't know, 10 times faster, mostly because to show it being 100 or 1,000 times faster, it would take a long time to run the first experiment. And I don't want the VOD or the stream to take that long. But as a homework assignment or a thought experiment, I want to leave all of you with the question on which do we think is going to be more efficient in the second piece. So foregone conclusion, we know what the outcome is here. We know this has to be at least as fast, if not faster than this. Logically, it can't possibly be anything else. But this one, it's more nuanced. This raises some very interesting questions. Now, I don't even want to tell you how to think about this because I feel like that's me kind of giving you the answer. Instead, what I want to do is leave it at this and know that this is what we're really comparing. We're comparing against this original structure, which had these -1s, versus this modified, which eliminates the -1s and changes it to less than or equal to. We have a high degree of confidence that these are semantically equivalent. They're basically saying the same thing, but they move the mathematical operations around slightly. The question now for all of you is, which is more efficient based on the principles of mathematics and the way that those mathematics are implemented in programming languages? And I think if you have mastered the basics of both mathematics and programming languages, you likely will be able to observe or have a strong intuition of which one is going to be more efficient or less efficient or equal without even running any experiments. You'll be able to just think in your head and say, oh, Goju, I've got it. It will be this way because of these things. And it'll just be purely logical. So I'm going to leave it at that. And for the next stream, which I might do later today, depending on if I'm, if I have enough. These are my lifesavers today. I'm feeling a little bit better in a few hours. I'll continue this, and then we'll deep dive into this, and maybe we'll actually run these 2 variants of code, and then we can see empirically. In fact, what we'll probably do is run the original code, and then the second version will be just this change. We'll leave this code the way it is. And then the third variant will be to have this change. So we'll have what is known as a proper ablation proper ablation experiment. Okay, that's basically what we're talking about here. This thing. Okay, it's well, usually the way yeah, right. Okay. A research method where parts of the system are systematically removed or altered to observe the impact of the system's overall behavior or performance. So I tend to think about it as single variable alteration, and you want to do controlled ablation experimentation to understand the impact of the changes that you're making on the overall system, one variable at a time, so you know exactly what's changing. So this is this is an ablation study. So let me just make it super clear so we all understand what we're going to do. I'm really going to be on the hook for this now. Oops. All right, this is ablation study 2. And this is the third one, which is going to do this. There we go. These are the ablation studies that we're going to do. It's essentially experiment number 1. This will give us some performance numbers. This is experimentation number 2. This will give us different performance numbers with just a single augmentation, single improvement that is applied twice, but it's the same principle that's being incorporated. And then ablation number 3, which is to incorporate the third change. Excellent. Okay. With that, thanks everybody. I think we're done with this stream, and feel free to drop any comments on what you think the answers are in the comment section. Otherwise, we will take a look at the actual performance results of this in the next stream. Okay, thanks.